Hi guys, welcome to a lesson of partial differential equations. So in this class, we are going to discuss one-dimensional homogeneous wave equation with the homogeneous boundary conditions. So we will discuss Drichlet and Neumann boundary conditions in this lesson. So here we are given with an equation that is homogeneous wave equation. All right. So the boundary conditions are given as well, that is u of 0 comma t is equals to 0 and u of l comma t is equals to 0. So we can see that these are the Drichlet boundary conditions and they are homogeneous. So because the both ends are fixed at 0 0, and here we can see that the initial conditions are given as well, initial displacement and initial velocity. So again, we are using the same concept of separation of variables. So here we separated the variable by using the product function. Then we will calculate u double t and u double x, and we will generate the equation in this form, and we'll equate with lambda, and then we will solve for three cases, right? As we did in the case of heat equation. So here for the first case, when lambda is equals to 0, we know that this is the solution for x, and now this will be the solution for t, right? So the difference between the wave and heat equation is that we have a second derivative of both functions, that is for function of x and function of t. All right, so here we will apply the boundary conditions. We are given with x 0 is equals to 0 and x of L is equals to 0, right? So we'll apply the boundary conditions, and here we can see that we get C1 and C2 is equals to 0. Therefore, this is the trivial solution. U x comma t will be equals to 0, right? So this is trivial solution for case 1. Now we will check for case 2. So for case 2, we will take lambda greater than 0. Therefore, we take lambda is equals to p square, and then we will construct the solution and then apply the boundary conditions, right? So here it will be a second order ordinary differential equation, and we know how to construct the solution for the second order ordinary differential equation, right? So the equation will be in this form: x double prime is equals to p squared x. Then we will solve for the auxiliary equation, and then we'll find this solution, right? So this is the solution for x and this is the solution for t. Now we'll apply the boundary conditions, and we can see that there are two equations for C5 and C6, so we can solve it simultaneously to get the value of C5 and C6. So both the equations are homogeneous, so it's a system of linear homogeneous equations. Therefore, the solution will be trivial, right? So C5 is equals to C6 is equals to 0. Therefore, the solution for the wave equation for this case is also trivial solution, right? Now we will check for case 3. So for case 3, we know that lambda is less than 0, and we will take lambda is equals to negative p squared, and then the equation will be of this form: x double prime is equals to negative p squared x, and t double prime is equals to negative p squared alpha squared t. All right, so from here we can solve these equations, differential equations, and we will get the solution, and then we will apply the boundary conditions. So from the first boundary condition, x of 0 is equals to 0, we get a is equals to 0, and for L, x of L is equals to 0, we will find the eigen value for this equation, right? So we are already familiar with this phenomena, that sine PL is equals to 0, therefore PL is equals to sine inverse 0, and sine inverse 0 is equals to n pi. All right, so this will be the eigenvalue for this problem, right? So we said that lambda is equals to negative p squared. So n squared pi squared over l squared with the negative sign. This is the eigenvalue for this problem, this case, and then we will generate the eigenfunction. So here x of x is equals to b sine n pi x over l, and t of t is equals to c cosine n pi alpha t over l plus d sine n pi alpha t over l. All right, so we will generate the general solution for this problem by using u of x comma t is equals to x times t, right? So this is our x and this is our t. So we will multiply these functions and now we will get this form. All right, so we can separately multiply this sine n pi x over l with both of these functions. So here we multiplied bc sine n pi x over l times cosine n pi alpha t over l, then plus bd sine n pi x over l times sine n pi alpha t over l. Right, so we are calling that bc is equal to summation n is equals to 1 to infinity bn, and bd is equals to summation n is equals to 1 to infinity an, right? So here now the solution will be in this form. Right, now we can apply the initial conditions to find these constants bn and an. So we will use the initial conditions, that is u of x comma 0 is equals to f of x, and ut of x comma 0 is equals to g of x, right? So we will use both these conditions to find bn and an. When we'll apply the first condition, we will get a bn by solving for the Fourier series. All right, so we'll get bn, and then we will apply second initial condition, that is initial velocity condition, and we will again use the sine series to find an, right? So we will find the derivative first for the equation, general equation, and we will plug t is equals to 0. This is the derivative, right? When we plug t is equals to 0, this whole function will be equals to 0 because of this sine 0 here. This will be 0 because of sine 0. All right, so this we will get only this function, right? We will equate with g of x, then we can find by integration as we did in the Fourier series, right? Now we can construct the general solution, and just we have to plug bn and an for the function if the functions for the initial conditions are given, right? So this is the way to construct the solution for Drichlet boundary conditions for homogeneous wave equation. Right now we will discuss Neumann boundary conditions. So now we are going to work on the Neumann boundary conditions, and we know that the Neumann boundary conditions are the derivative boundary conditions. So for this wave equation, we are going to work on the Neumann boundary conditions, and we are going to see that how we can construct the solution for this problem. The initial conditions are also given, the initial displacement and the initial velocity, right? So the idea is same. We are going to separate the variables by using the method of separation of variables, and then we will apply three cases on the problem, right? So here is the case one, that is for lambda is equals to 0. This is the solution for x, this is the solution for t. We will apply the conditions. The boundary conditions are x prime of 0 is equals to 0, x prime of 0 is equals to 0, and x prime of L is equals to 0. Now it means that we are going to find the derivative of x, and then we are going to apply the boundary conditions. So here this is the derivative c1. So from this derivative we can see that we only get c1 is equals to 0, therefore c2 is any arbitrary constant, right? So now the solution we know that it's equals to x times t, right? So x is now c2 and t is the whole function, that is c3t plus c4. Therefore, this will be the solution for this case. And c2 times c3 is just a constant. Therefore, we can write c2 times c3 is equals to a and c2 times c4 is equals to b. All right, so the general solution for this case will be uxt is equals to at plus b. So this is non-trivial solution, right? This is non-trivial. So this is going to work for us. And now we are going to check case 2. So for case 2, again, we are going to differentiate the function for applying the boundary conditions on x. So the equation for x double prime will be equals to p squared x. And by using the auxiliary equation, we can generate the solution for x of x. So here we are going to find the derivative to apply the conditions. And now we will apply the conditions here, right? So you can see that we have system of homogeneous linear equations, so we can solve them simultaneously to find the value of c5 and c6. Therefore, when we will solve these two equations, we will get c5 is equals to c6 is equals to 0, which means that our solution is trivial for this case, right? So this is not going to work for us. Therefore, we are moving to case 3. Now case 3 is when lambda is equals to negative p square, which means that lambda is equals to less than 0. So the equation for x double prime will be negative p squared x, and equation for t double prime will be negative p squared alpha squared t, right? So now we will find the solution for this differential equations, these, and then we will find the derivative to apply the boundary conditions. Therefore, we will apply the conditions and we will get b is equals to 0 from the first condition, and we will get sine PL is equals to 0 from the second condition, which will give the eigenvalue, and then we will plug this eigenvalue in the function of x, and then we will multiply to construct the general solution. So here we can see that u of xt is equals to at plus b, because we are using superposition principle. This part is from case 1, that is for lambda is equals to 0, and this whole part is from lambda less than 0, right? So we are going to use the superposition principle for this. And now we can write for AC sigma n is equals to 1 to infinity an, and for AD sigma n is equals to 1 to infinity bn, right? And then this will be the general solution. So now we are going to apply initial conditions on the problem. So the first condition, that is u of x comma 0 is equals to f of x. It means that at t is equals to 0, there is some function of x. The behavior of the wave equation is given by some function of x at t is equals to 0. So when we will apply t is equals to 0 to the equation, we will left with b plus summation an cosine and pi x over L. So this is equals to f of x. So we can now solve it by using the Fourier series. So we can see that this is a cosine series, right? So for b, we can write half a naught because b is a constant. So we can write it in this way. So to make it compatible with the Fourier cosine expansion, to apply the expansion effectively, therefore this will be half a naught plus summation an cosine and pi x over L is equals to f of x. Now we know that how to find a naught and an from the lesson of Fourier series. So we are going to integrate from 0 to L the function of x for a naught and the product of function of x and cosine and pi x over L for an. And then similarly for the second initial condition, we will find the derivative, that is the initial velocity. So then we will left with this function a plus summation n is equals to 1 to infinity and pi alpha over L bn cosine and pi x over L, right? So this n pi alpha over L comes because of the derivative, right? So now we can put a is equals to half b naught again to make it compatible with the cosine expansion. So here now this is the equation for cosine expansion. So, right, so it's equals to g of x, and we can find b naught and bn, right? So when we will find b naught and bn, then we can plug all these values in the general equation to find the particular solution for any function of x and g of x given as initial conditions, right? So this is the idea, and at last you have to plug a naught is equals to 2b, because in the assumption we assume that b is equals to half a naught, so you have to plug it back for the original solution, right? So this is the idea for the homogeneous boundary conditions. So you can solve any problem easily when homogeneous boundary conditions are given for the homogeneous wave equation, right? So in the next lesson we will come up with the uh, idea of non-homogeneous wave equation with the homogeneous boundary conditions, right? And we'll talk about some mixed boundary conditions. So that's all for the time being. Thanks.